One of those chapters. 14? That sounds good. Why not? Let's go with that chapter. Seems good. All right. So pretty much in this chapter, we had all the remaining organicness. And if I could remember, I would tell you what that was, but I think there's some carboxylic acids. I think there was some esters, which looks like a carboxylic acid. Then we got into some nitrogen-containing groups here, and we were in the middle, I think, or towards the end of talking about amines. Amines are, again, this sort of nitrogen-containing group. They're basically sometimes referred to as derivatives of ammonia. And amines, much like some of the other organic guys that we've talked about, alcohols, carbons, and so forth, we can classify as primary, secondary, and tertiary amines. Again, a primary amine would have one carbon attached to it. So something like this. Secondary amine would have two carbons attached to that nitrogen group, like this. And a tertiary amine would have three carbons attached, such as this. You can see every time we sort of attach a carbon, we do take out a hydrogen, right? And remember, on the sort of nitrogen ones, a lot of times they are not drawn, but there are those non-bonding electrons on the nitrogen. And again, that's what gets it to sort of its 8 electrons that it needs for the octet rule. I think we said we're going to go with a kind of common name for these guys. So we'll go common name on these guys, which basically we just kind of name the groups that are attached. So very similar to how we name ethers, where we kind of go to the oxygen, look at what groups are attached here. Here we go to nitrogen, look what groups are attached. So obviously here we have a methyl group. So this is methylamine. Basically just put amine at the end of it. This one here would be two methyl groups, so a little dimethyl amine. And here, since I got super creative and just went with three methyl groups there, that's going to be a trimethyl, right? Amine in this case. Obviously, if you had different groups attached, we still go alphabetical order in terms of the groups. Again, regardless of the prefix. So I think we saw maybe a couple last time where there was like a methyl and maybe an ethyl involved. And again, the ethyl would go first there, comparing the E to the M in the methyl group. Also, something sort of, I don't know if you call it weird or a little bit different in terms of when we do have nitrogen containing groups, and we actually do have sort of groups attached to the nitrogen. We sometimes will use an N. So I think we saw it when we were talking a little bit with aniline here. You know, that's aniline, right, which has the NH2 on the benzene ring. And again, if we had a group sort of attached there, like a methyl group here, still have a hydrogen going on there. This would be still aniline here. And again, the methyl group is attached to the nitrogen, not a carbon. So as we talked about, I think last time, sort of numbers are reserved for carbon groups that are attached to carbons. So here, this would be something like, you know, N-methyl and then aniline. And again, the N basically just means instead of it being attached to a carbon, it's attached directly to a nitrogen. Also, you could also have kind of like when we have two numbers, like 1, 1 or something like that, you can have like an N, N where you'd have two groups attached to the nitrogen. So again, that's sometimes you'll see that with secondary and maybe tertiary amines. So sometimes happen in that case. Any questions on any of that there? All right, so we touched upon some of this, but again, you could obviously draw a line structure like normal. And again, here we got 1, 2, and 3. And that is where the propyl comes from. And once again, there's our amine group there. So our propylamine. Here we have our two groups attached. Again, just kind of going with the nitrogen left and right of it, I guess. 1 and 2 is an ethyl. 1, 2, and 3 is a propyl. Again, in alphabetical order, ethyl, propyl, amine. And here's like kind of like the one I just did earlier. Ethyl group there, and a methyl group there. And that gets us diethyl methylamine, which is again our tertiary amine. Now, in terms of solubility of amines, because they are ammonia based, they have really a lot of the characteristics that are able to hydrogen bond. And if you remember, what you need for hydrogen bonding is basically a hydrogen that's directly attached to a nitrogen, oxygen, or fluorine, right? And since in this case, the amine group is this group right here, that definitely qualifies, right? For our primary and secondaries, they have a hydrogen that is directly attached to the nitrogen. So it does give it the ability to hydrogen bond. And because of that, primary and secondary amines will be soluble in water, kind of very much like everything else that could hydrogen bond with water, like what we saw with alcohols and some others. Again, when you get to that sort of magical number of 5 or 6 carbons, solubility really does start to decrease for all the same reasons we talked about before. As you get, again, a lot bigger R group or carbon group, the non-polar part of the molecule again gets too large and it prevents it from interacting well with water, even though it has the ability to hydrogen bond. Tertiary amines cannot form hydrogen bonds with water, and that is because what is it missing to do that? A tertiary amine looks something like this. It's kind of missing the hydrogen, yeah? So it doesn't have the hydrogen, a tertiary amine, to hydrogen bond with water. Primary, which looks like obviously this guy here, he's got a couple of hydrogens could do it. If you get to a secondary, we'll just draw a very simple secondary here. He's still got the hydrogen there, so he could still hydrogen bond. But again, kind of when you get to that tertiary, you kind of lose that hydrogen there, and it's not available, obviously, to hydrogen bond. So we see a lot of solubility, obviously, with primary and secondary. And tertiary, again, not going to be as soluble, obviously, as well. Because amines do contain that nitrogen-hydrogen bond, they will do that hydrogen bonding. Tertiaries do not have that hydrogen on the nitrogen and can only form hydrogen bonds with water from the nitrogen. So it can hydrogen bond with water, but it's limited with the water having to supply kind of the hydrogen in that case, as opposed to it supplying the hydrogen, which would be a lot more easier for it to interact. So again, in this case, if you had water, which this is more negative, this is more positive, in a tertiary situation where we have this basically. In this case, this guy's going to be more negative and it's going to be able to hydrogen bond through that way. Again, with the water kind of supplying it. That is a lot different than, again, a secondary or primary that can use its hydrogen to actually, for example, hit up there at both spots, right, with a water molecule. So it can hit the oxygen with its hydrogen and it can still do the hydrogen to the nitrogen on the other side. So that gives it a lot more interaction with water, right? Going to make it a lot more soluble, primary, secondaries than, say, tertiary ones. Like alcohols, the smaller the amines, including tertiary ones, they are going to be soluble in water because they can form that. But again, our primary, secondary can be a lot more soluble. If the amines are more than 6, the effect of hydrogen bonding is diminished, just like normal. Again, just for example here, this is just a lot of non-polarness all around that nitrogen. So again, it's going to sterically hinder or get in the way of water being able to interact really well there. So you're probably not going to see a lot of solubility in comparison to something that doesn't have a lot of those carbons there. All right, so take a moment here. Which one of these should be soluble in water? Okay, so looking at this here, this is a primary amine, right? We got our amine group there, one carbon directly attached to it. It's got a couple of hydrogens, so it should be good to go in terms of it's being soluble in water. Less than 6 carbons on there as well. That's sort of helpful. This is a secondary amine. Again, this nitrogen is attached to 1 and 2 carbons. Still has the hydrogen available to it, so that also is going to be pretty good and no problems. Bottom one is not an amine. That's a good old alkane happening there. That's nonpolar all day, right? Which means it's not going to be soluble in water, right? Again, it's going to try to use dispersion forces, and water's going to try to use obviously hydrogen bonding, so that's not going to work well. Again, it goes back to that sort of like dissolved likes, things that use similar type of intermolecular forces that they use with themselves will be soluble in other things that use similar type of forces. Any questions on that one there? All right, so let's talk a little bit about some reactions amines do. And because they are really ammonia sort of derivatives, ammonia is a weak base. So not surprisingly, maybe they will act as bases with water. And this is again going to be our Bronsted-Lowry definition, much like we talked about. We're going to get our water here acting as the acid, our amine acting as the base, and we're just going to send over our H plus basically over there. That's going to get us our conjugate partners. This would be our conjugate acid, and this would be our conjugate base over there. So because they're really like ammonia derivatives, they will do a basic sort of acid-base Bronsted-Lowry reaction. And that's for primary and secondary ones. Will basically do that. Amine salts are formed. They're responsible for some of the odor that you smell on fishes. Again, amines react as Bronsted-Lowry bases in a neutralization reaction with some citric acid that you might squeeze on there. And we can do an acid-base reaction as well. And again, here our amine is going to act as a base. Here's our regular old hydrochloric acid. Same deal is going to happen. It's going to send the H plus over from the acid. That's going to give us really a salt here. We just don't make a salt and water. So before we had like an acid-base reaction, make salt and water. Here we just really make the salt part. The salt just a fancy word for this two things because it has an ionic compound basically. So we got a negative charge and a positive charge, but we're basically just sending the H plus over there. Here, same deal. It's going to happen. We're going to send our H plus over. And again, we're going to add our hydrogen, much like we talked about when we did Bronsted-Lowry sort of reactions. Remember, it's not just the hydrogen, but the charge is important. So it gains the positive charge and becomes one more positive in this case. And we do end up with basically the exact same thing, except for an H plus basically added to it. The chloride here comes from the HCl. So when that comes apart, you know, that is what is left over. This guy heads over there, basically. Yeah. Amines are usually converted to ammonium salts before being used as drugs. Ammonium salts are solids at room temperature, odorless, and soluble in water and body fluids. So a lot of amines are in some medications. As you can see here, ephedrine here is our amine. We also have our amine over here as well, and then Benadryl. Some more over here in cocaine. So we have some amines happening, you know, and we also have our amine over here as well. And it does, again, an acid-base sort of reaction occurring here, making our sodium chloride as it continues on to make that there. Alkaloids are physiologically active compounds produced in plants that contain nitrogen. So for example, there's nicotine as well, basically an amine-based, adrenaline in the blood increases that levels. And again, there's basically our amine in this case. That's actually a tertiary amine, right? Carbon there, and carbon there, right? Attached to our nitrogen group. Caffeine as well. You got a lot of amine that going on in there. Coffee beans, tea, chocolate. So these amines are found in a lot of places. And morphine as well is also amine based there. All right, so once you draw the structures for each of these here, methylpropylamine and 2-chloroaniline. Okay, let's take a look. So again, on these amines, I personally sort of draw them like we draw our ethers, which is in this case, instead of starting with the oxygen, I'll start with the nitrogen, because that's obviously our functional part. And then really just kind of draw our groups to either side. So propyl is 3, so I need 3 carbons, and methyl is 1, so I need 1. At this point, I could add my hydrogens here. And I do need to remember, though, that my nitrogen needs 8, right? So I do need to actually add a hydrogen there to my nitrogen, otherwise it's short. That's the condensed. If I was going to do the line, I would do the same thing. I would start with the N. I would go a little 1, 2, 3, and just a 1 maybe, and a hydrogen in there as well. Any questions on that one there? Yeah, you can. It's okay. Yeah, yeah. You can actually do it on the, if you're talking about here, you can put the H there. It's okay. Yeah. Other questions? All right, so aniline is again that benzene ring that has the amine group on it. And in this case, this is 2-chloroaniline. 2-chloral means the number 2 is on the carbon, not the nitrogen. So again, if it was on the nitrogen, it would say N. So here we actually have a number, which means we do know that that has to be carbon number 1, and it really is your choice, whichever way you want to go. I'll go this way, and I'm going to put my chlorine there, but you could have went to the left as well. It would be fine. And you could also put the NH2 pretty much on any carbon you like off of the ring. Any questions on those there? Okay. All right, then let's talk about the final organic group, which are amides. And as you can see here, part of acetaminophen. And these guys are pretty much like a combo of like a carboxylic acid and an amine. And you can see the functional group here is basically this right here. That is the functional group there of an amide, carbon oxygen double bond, and really like an amine group on it, a nitrogen containing group. So it's kind of like a carboxylic acid without the oxygen. It's got nitrogen instead in this particular case. And that's what you can see right here. That also is a peptide bond that makes between amino acids. That's pretty much that bond right there when you do it. And as I just mentioned, that's essentially how we get there. We have a carboxylic acid and we have an amine, and maybe probably no surprise here, but we're just going to take out water basically and stick these guys together. So if I were to turn this guy around a little bit here just to show you, we'll do something like this. And then I'll turn this guy around. Yeah, I got that going in this direction. And basically we're going to take out water. So, I mean, it's your call as to sort of how you want to take the water out. And then for our purposes, it doesn't so much matter, but you could just kind of take a water out right there if you want, 2 hydrogens and an oxygen. And all you're going to do basically is just squish it together, and you will get basically what is there. And we'll go this way. We got rid of that. We're going to do our amide connection there. And again, nothing else is going to change. And we'll end up with our amide right there. That's connected, although I did draw this hydrogen up on top. It doesn't really matter. Questions on that there? So once again, here you can see it. We're going to basically put it together. We're going to take out water, and that is the water that comes out. And we basically just squish these guys together. So Much like kind of like the ester, I would recommend, if you can, maybe turn one around and kind of line up the water and then just take out the water. And then at that point, if you have it lined up like that, you could just squish both sides together and just make sure you make that connection. The connection should always be this connection here, which is our amide connection right there. Again, the carbon to the nitrogen connection, obviously with the appropriate stuff that's going on there. As you can see, the way this is named is a couple of different ways, but the good news is we're not naming it, so don't worry about it, I suppose, right? So you don't have to worry about naming amides. You do need to know, obviously, what they come from. Again, a carboxylic acid and a amine. Amides, as we can see here, what's going to happen in this case, once again, is I would probably recommend just turning this guy around if it helps you draw out the hydrogens. And now what you could do again is just take out your water. Don't really matter which hydrogen you snag. You can just take out your water in that particular case. Once again, nothing else is going to change. We're just going to squeeze everybody together. So once again, nothing fancy happens here. Everybody stays the same. We'll get our carbon oxygen double bond. We obviously have taken out our water here. I'll just sketch it out. We're then going to make our amide connection there and just squeeze it together, basically. Any questions on that there? Go. So naming amides is, for another day, which will never come in this class. What is a common name? You don't care. I don't care. We're just moving. All right. So again, you need to know the functional group of an amide. You don't need to name it. You do need to know, be able to recognize it. Here again, urea is an amide, as you can see there. Again, here is our amide connection. The end product of protein metabolism removed from the blood by the kidneys there. Barbiturates as well. Again, you got your amide group going either way, actually, on that one, as you like. Aspirin as well. Again, there's our carbon oxygen double bond with our nitrogen happening here. Now let's talk about two reactions that amides undergo that you do need to know. So one is kind of similar to what we saw when we talked about acid and base hydrolysis here. So let's start with the acid hydrolysis. Again, in this case, we're going to have some water and an acid involved and maybe a little bit of heat happening. And in this case, what's going to happen is we're going to basically break it apart. So we took water out to make it, and to break it apart, we're going to kind of put water back in. And it may not be a surprise, but it is going to break apart right where we put it together. So this one is this guy here, CH3, C double bond O, nitrogen, hydrogen, and two hydrogens, I think. And we got some water happening here and an acid as a catalyst. So we do put it together. So once again here, it's going to break apart right there where we obviously put it together. And again, as I mentioned, we got it by taking water out. So we're going to actually put water back in this case. And we're going to end up with, as you can see there, we will get the carboxylic acid back. So gotta do it there. I think we'll get this part here. And I'll go underneath. And then our other part, obviously, here, right? So at this point, we do, again, the good way to remember this is the acid hydrolysis. So you do get the carboxylic acid back, right? So the acid gives you the acid back. We're going to borrow the OH there to do that from the water. And if we do that, that is how we're going to get our carboxylic acid back. At this point, what's going to happen is we're going to add on our hydrogens that are left basically to our nitrogen, and we're going to get actually ammonium chloride here. We're going to get kind of a salt that's going to happen. So we get a salt, And we do get the carboxylic acid back when we do the acid hydrolysis of it, and almost get it back in this case. Any questions on that one? The base one, as you can see down here, will involve a base being used. We again are going to break it apart here. We are also going to still get the two parts. They're going to be pretty much the same. So we're just going to copy what's there. And then we'll copy the other side here. Now, in this case, we have only sodium hydroxide, so we don't have all that extra hydrogens to kind of replenish everything where we have within the acid situation. So in this case, we're actually only going to get back a carboxylic acid salt. We're only going to borrow the oxygen here. And that is what's going to end up over here on this guy. So we won't get the carboxylic acid back, but we'll get that. We also, if you just want to kind of keep track, we have also a hydrogen there. And we're going to get us a hydrogen that's going to come back over here. That also will be an H plus, which will give that a charge. And I'm sorry. And that would be it, actually. We won't get that charge there. We'll just get the hydrogen back. And we will have our amine back. So the way to sort of remember this is we get in the acid one, we get the carboxylic acid back. And in the base one, we actually get the base back, which is the amine in this case, right? Amine very much like a weak base. So base one, we get the base back. Acid one, we get the carboxylic acid back completed. And then we basically get salt on the other one. So kind of the leftover pieces is basically what we get. Any questions on that there? All right. So taking a look here, this is the base hydrolysis, another example. So base hydrolysis, gonna break apart. Base means we're going to get the amine back completed, and here we're gonna get more of a salt that's going to happen. So the oxygen is gonna end up over here, giving us a negative charge, and the hydrogen will end up over here to give us back our amine and stuff. So in this case, the hydrogen goes to the base. Everybody else there goes over to the carboxylic acid. All right. We don't care about that. There it is. Now to chapter 13, which is carbohydrates. So pasta, some bread, some good stuff maybe. All right, so let's talk about hands. Those are hands. These are chiral molecules. So a chiral compound is a compound that basically has a carbon attached, and attached directly to that carbon are 4 different groups. So in order for something to be chiral, it has to have 4 different groups attached to a carbon. As we will see, there'll be some multiple, perhaps, chiral carbons in a carbohydrate. And chiral compounds have a mirror image that does not superimpose on each other. So what that means, for example, is the hands there. If you put this hand up to the mirror, you get this hand staring at it, right? And if you pull the mirror image out, you could do whatever you want with the mirror image. You could rotate it, you could move it around. You will never be able to superimpose on the original guy perfectly. So even though I could do this and my thumbs are okay, one's palm up, one's palm down, so that's not good, right? If I go this way, thumbs on the wrong side, thumbs, everybody's palm down, but thumbs on the wrong side. So what a chiral compound is, it has a mirror image that is not superimposable. Again, you could try to rotate it as much as you want, but it will never be able to fit perfectly. There will always be something that is slightly off. And usually what happens in that case is it kind of makes a mirror image makes a slightly different connection than it has in the original guy. And that's what we see here. Mirror images, chiral compounds cannot be superimposed. So if we take this guy and stuck him up to the mirror, and we take, again, this entire mirror image out and try to put it on there. And again, it may be hard to visualize, but you could just think you rotate it around, but that is tetrahedral geometry, which means they're spaced out, not as perfect turn, right? We'll do it 109.5 degrees. So there will always be something that will not match up, as you can see here. Although we could get two of the four to match, we're not matching here. So again, those mirror images will not superimpose, and that would be a chiral. This right here in the middle, which is a carbon, that would be what is known as a chiral carbon. And again, it has basically four different groups attached: a hydrogen, a chlorine, an iodine, and a bromine. Four different ones attached to that carbon makes it a chiral carbon. And since that's the only carbon in that compound, it's a chiral compound as well. Now, different than that is an achiral compound. An achiral compound you can put up against a mirror and take the mirror image out, and it will actually superimpose. So a difference between chiral and achiral is an achiral compound does not have four different groups attached. So for example, here we got a couple of BRs there, right? The same group attached to the carbon. And because of that, when you spit the mirror image, you got one that all you have to do is rotate and you'll be good to go. It's going to actually fit perfectly on there. So achiral mirror images will superimpose. Chiral compounds that have four different groups attached to the carbon will not superimpose. Here are some examples of chiral and achiral. Gloves, obviously, like hands. Golf clubs, achiral is a soccer ball. And shoes, obviously, are achiral as well, are chiral as well. All right, so take a moment for each of these. Are they chiral or achiral? Look, so if we look here at the center carbon, that is a chlorine, which is different than a hydrogen, and those two are different than a ethyl group, and that is different than a methyl group. So that is four different groups attached to that carbon, so that's going to be chiral in this case. If we take a look at the middle guy, that is a chlorine that's different than a hydrogen that is the same here, right? And because of that, that's going to be achiral in this case. And here we look at the carbon, methyl, bromine, hydrogen, and chlorine. That is 1, 2, 3, and 4 groups that are different. That's going to be a chiral compound here, since it has a chiral carbon. Any questions on that there? That's good. They agreed. Let's talk a little bit about our Fisher projections. So sometimes you'll see things drawn kind of two-dimensionally to try to represent three dimensionals. We oftentimes will place the most oxidized group up on top. We use sometimes vertical lines in place of dashes for bonds that go backwards. So sometimes you see something dashed out, like that. It means it's kind of going behind the page. Horizontal lines in place of wedges. Wedges, sometimes you would see kind of coming forward out of the paper. So we sometimes will see that sort of drawn more, which is solid lines and vertical lines. So here, as you can see, we have a mirror image. And once again here, this is a chiral carbon, as it has one group, two groups, three groups, and four groups that are attached that are different. So again, our mirror image here are going to not superimpose. And here is very common how you see carbohydrates written almost like intersections of lines, almost like line forma, if you will. So every place there's sort of an intersection is a carbon that's there. Again, kind of like in organic where you have the line structures happening. So that is our chiral carbon right there, which is the same guy that's above. And that's, I would say, most commonly how you probably will see a lot of them written more like that sort of structure. Now let's talk a little bit about some notations that we also see, which are D and L. By convention, L means left, I'm assuming, and D means right. I don't know, they could have used R, but they used D instead. And what are we talking about here? We're actually talking about the OH group on the last chiral carbon from really the carbon-oxygen double bond. So when you look at a carbohydrate, it oftentimes will have a carbon-oxygen double bond somewhere. We're looking for the very last chiral carbon from that down the road. I would say probably 9 times out of 10, or maybe even more. If you find this guy on the bottom, just go one up from it, and it most likely is going to be your last chirocarbon. Not 100% of the time, but most of the time, that's where you can kind of find your last sort of chirocarbon down the chain. In this particular case here, our OH on that carbon is on the left, so that is L-glyceraldehyde. And over here, obviously, our OH group there is on the right, so that is our D sort of conformation here. And again, that's what you're looking for to decide if it's, for example, L or D. Isomers of each other. All right, so take a moment here. Can each Okay, so really what we're looking for is are these a chiral compound or not, right? Because that's going to tell us can it be superimposed or not. So we'll take a look here at the carbon. I got methyl, that group, and that group. That is 4 different groups. That means this guy is chiral, which means its mirror image over here as it gets projected, if that was the mirror, will not be able to superimpose. So for the question is, yes, this is the one that will not be superimposed, right? But to answer the question would be yes, the answer is that one. The bottom one here, we have an achiral situation happening, right? We got a couple of hydrogens, and that means that actually this mirror image here can superimpose with a little bit of rotation, and you'll be good shape. I guess can be superimposed. I'll just answer it that way. Any questions on that there? Yeah. All right, so let's talk a little bit about carbohydrates. Carbohydrates are a major source of energy from our diets. They are composed of carbons, hydrogens, and oxygens. They're called saccharides, which are sugars. And we talk about some different types of sugars here as we go through it. And carbohydrates are produced through photosynthesis in plants, such as glucose, and synthesized from plants from CO2 and water, and this nice little respiration type cycle happening here. And all oxidized and living cells will produce CO2 and water. So this nice little circle there with a little bit of sun help there produce some carbohydrates. Now, there's some different types of carbohydrates we're going to talk about. We're going to talk about monosaccharides, and monosaccharides are the simplest carbohydrates you could have. Mono meaning one, they basically come as ones. We'll have disaccharides, which are basically a combination of 2 monosaccharides put together. I don't want to ruin it, but you basically put water or take water out and put them together. So you could kind of stack them by taking water out and stacking some carbohydrates together. And that's also how we get to polysaccharides, which are just a bunch of repeatable sort of carbohydrates all put together by basically taking out water and sticking them together, basically. Let's start with some monosaccharides. Now, monosaccharides consist of 3 to 6 carbons, and they have basically one of 2 organic groups up on top. They either have an aldehyde group or a ketone group, and these are the same organic groups that we talked about. So some carbohydrates will have this aldehyde group, and some carbohydrates will have our 3 carbon run with our oxygen in the middle and our ketone group. So they'll have these same sort of organic groups that we saw. And definitely they'll have a bunch of hydroxide groups or hydroxyl groups or OH groups, basically a bunch of those on there as well. So let's take a look at some of these here. The first type of monosaccharide is an aldose, and aldoses kind of sounds like aldehyde, and that is because it has the aldehyde group up on top. So aldoses will have the aldehyde group up on top, and it's on top because it's much like what we have with organic chemistry. It still has that hydrogen at the end, right? Which means it can't be inside. It's got to be at an end. In this case, it's at the top of or one end of the carbohydrate in that sense. And it can have a different numbers of carbon atoms in it. And depending on how many carbon atoms it has, you can also classify it based on the number of carbon atoms. So triose means it has 3 carbon atoms. Tetros, like tetra, has 4. Penta, like pentos there, has 5. Hexa, like hexos there, has 6. So this particular one is an aldose because of the group that is there. It also has 1, 2, 3, and 4 carbons, which is why it's a tetros. So this is sometimes referred to as an aldotetros. Again, aldo because it has the aldehyde group on top, and tetros because it has the 4 carbons. Now, very similar to sort of organic chemistry in a sense, if we were numbering our carbons, we do give priority to that functional group. So if we were numbering our carbons, this would be carbon 1, this would be carbon 2, this would be carbon 3, and this would be carbon 4. And again, much like we do in organic, kind of give that guy the priority. That's how we would kind of number these carbons. By the way, how many chirocarbons are there in this guy? Are there any? The answer is there are actually. So let's take a look and see. Let's take a look. Obviously, this is our functional group, and it doesn't have 4 things attached really, so it's always not going to be chiral. This carbon is a chirocarbon, and it's because it has this OH group, it has this hydrogen, it has this entire thing, and it has that entire thing as well. So those are the 4 groups that are there. Now that I made a mess of that drawing, let me erase those and blank out the screen. And then let's take a look at the next one. So if we come to carbon number 3, carbon number 3 has an OH group, an H group. It has this entire group now, and it has this entire group, which is also 4 different things. And that would also be a chirocarbon as well. So carbon number 2 here and carbon number 3 here are chirocarbons. What about lucky carbon number 4? Is that chiral? It is not chiral. If we were to kind of draw it out, right, it has everything above. It has an OH and it has 1 hydrogen and 2 hydrogens, right? So typically, if you see this CH2OH on these carbohydrates on the bottom, typically not a chirocarbon. And that's why I said in most cases, just go up 1, and that would be the very last chirocarbon in the chain. So this one does have 2 chirocarbons, carbon number 2 and carbon number 3. This is a L or D? It is a D because we're looking at the very last chirocarbon. And here the OH is on the right-hand side, right? Which means it's a D, not an R. But you get the idea. Any questions on that there? Okay. Now we could also have ketoses, which are different than aldoses. And the difference is it's got really the ketone functional group here. So much like we saw in organic chemistry, that's our ketone functional group. And just like we saw with organic chemistry, that means the carbon-oxygen bond, that carbonyl carbon, cannot be at the end, right? It needs that 3-carbon run. So the farthest you could get is you'll always find that really carbon number 2 in this case, because it's got to be that 3-carbon run. If we were numbering, we would number this way: 1, 2, 3, 4, 5, and 6. That is a ketose or a keto, and it's got 6 carbons, so that is a ketohexose. Again, ketose because it has a ketone group, hexose because it's got 6 carbons. And now you're gonna tell me how many chirocarbons it has? I agree with 1. Keep going though. I agree. It is 3. It is this one. This one and this one are the three chirocarbons in this compound. For the same reason, again, if you kind of go above and below, left and right, they're all different groups. And if you did that for all of those guys, I won't box them all this time, but you would have basically different groups. So we do have three chirocarbons. Again, this would be L or D. D, again, we want to look at the last chirocarbon away from the carbon-oxygen double bond as furthest away as can be. And again, the OH group here is on the right. So this would be a D. Any questions I'll have there? All right. So for each of these, aldo, keto, tetros, pentos, LD, what do you got going on? The hide group. So that's going to be an aldo because of that. And again, we just want to kind of count our carbons, and that where that carbon oxygen double bond should always get the smallest number. So that's going to be carbon 1, and then we just number downward here, 2, 3, 4, 5, and 6. In this case, we got 6, so that's going to be a hexose as well. This guy over here, that is our ketone group there, right? Our 3 carbons and our double bonded oxygen there. That's going to be a keto. Once again, we do want to give that guy the smallest number. So to do that, we got to go this way. 1, 2, 3, 4, and 5. And that's 5. So that's going to be a pentose in this case. And my guy over here has 1, 2, 3, and 4 chirocarbons, right? My guy over here has 1 and 2 in this case. And D and D. Yeah, on both of those there. Any questions on any of that there? Let's talk a little bit about the structures of some of these monosaccharides. As I mentioned before, when we draw these guys, we typically put the most sort of oxidized group towards the top. And again, that usually gets our sort of smallest number in terms of our carbons. And we do oftentimes will show our chirocarbons as a sort of intersection of lines. So again, remember that there is a carbon there, and that is going to be our chirocarbon in this case. And as we saw before, that is our last chirocarbon from the bottom. OH on the left-hand side, L, OH here on the right-hand side. And we have our D notation here. This one only has 1 chirocarbon, obviously the one that's pointing to in this particular case. As we see there. So here are some examples of some D and L, and I think you should be able to recognize this. Put a little star on this slide. You might not have to draw them, but you might need to recognize it. So make sure you kind of have some recognition of it. Glucose here, D-glucose. It is a 6 carbon. 1, 2, I'll just put circles around it. 3, 4, 5, and 6 carbon carbohydrate. D, this is our last chirocarbon that has the OH on the right. And again, pretty much that is a chirocarbon, that's a chirocarbon, that's a chirocarbon, and that would be a chirocarbon right there coming down. D-ribose, same deal. It's also an aldehyde. Again, it's got the aldehyde groups. Obviously, glucose is as well. And this guy's got 1 carbon, 2 carbons, 3 carbons, 4 carbons, and again, 5 carbons in this case. Here being our 3 chirocarbons, 1, 2, and 3 happening here, along with obviously our OH on the right, which gives us our D. Here is also a aldose. Also 1, 2, 3, 4, 5, and 6. And similar to glucose, except a little difference in terms of our OH groups, where they're located on which side. And this is our L, as our OH is on the left-hand side. in this particular case. And once again, chirocarbon there, there, and there is going to be a chirocarbon. Questions on that there? Can almost rattle off chirocarbons by looking at it, as long as on both sides of the carbon there's not like two H's or something like that, right? Then you'll know it's definitely a big chiro. Yeah. Yeah, so I would know it if it was given to you, maybe what it is. Yeah. Yeah. Other questions? But I write the final by next week. That would be good. But it's a good chance there might be a final happening. All right. So for each of these, is it D or L? Take a look and decide. Okay, so let's take a look. We're gonna always just kind of go farthest away from here, looking for the chirocarbon. Remember, these intersections are carbons. And since I see really different things on each of these sides, I know they are all really chirocarbons. And I'm looking for the last one, which also most of the time is about one step back from that guy on the bottom. Again, not 100% of the time, but most of the time it is. And that would mean my OH group here is on the left. So that would be L in this case. That would be an aldose and a 1, 2, 3, 4, 5 pentose happening. Here again, we're looking at our most oxidized group up on top. That's a carbon, that's a carbon, that's a carbon. Again, here, different groups there and there. So this is going to be, once again, my last one, OH there on the left. So that's going to be an L as well. And that is also an aldose and a 1, 2, 3, 4. So a tetrose in that case, right? It's got 4 carbons. This, though, is a ketose, right? We got a carbon. That is a carbon. Again, these are carbons as well. And that is where we get our 3 carbon run and our ketone group happening right there. And that's obviously a ketose. We also are going to be basically looking furthest away from there, which is going to bring us basically to this guy. And our OH group here is going to be on the right, which would give us D fructose in this case. Fructose, also a good one to maybe know. Yes. Any questions on that there? Yeah. Exactly. Yeah. Those are the actual names. Those are the actual names of it. When we talk about it being like an aldose or a ketose or a pentose or a hexose, that's sort of a description of what functional groups there and also how many carbons there are. But these guys have specific names, like you see. Those are the specific names, like ribose would represent that guy. It's a little combination, I think, of just some arrangement of it, to be truthfully honest with you. They kind of came up with it, but it is probably some of that, how many OHs and where they're located. So let's take a look at each of these kind of individually here. So we'll start with glucose, which again, you started the other one. You can start this slide. That's a good one. D-glucose, again, is found in fruits, corn syrup. As we saw there, glucose is its name, and it's an aldohexose, which describes, as we were just talking about, that it has obviously the aldehyde group, and it also has 6 carbons attached to it. It is blood sugar in the body, and it is the monosaccharide in a lot of polymers of starch, cellulose and glycogen, which we'll see later on. Which is basically just a bunch of glucose units stuck together, basically. We're taking out the waters. Glycogen, as you may know, right? Your body takes in the glucose, right? It goes through glycolysis, and it stores your stuff there as glycogen, which then you can break down through gluconeogenesis, right? And go through the whole cycle there to use it as energy if necessary. Now, when we look at blood glucose levels, in normal blood is 70 to 90. And obviously you could look at your levels, and kind of like when we talk about hypertonic solutions, hypotonic solutions, same idea. Hyper means more than, so obviously you would have a blood glucose level of more than. Hyperglycemia of normal blood glucose. Hypo would mean less than, and you would have less. And usually, obviously, if you take a blood test, right, it's oftentimes wants you not to eat anything, right? So you don't have the chocolate chip cookie right before you take it, right? Or the candy bar, and your glucose levels shoot up and stuff like that. So to get a pretty good reading, usually you want to kind of fast for a good amount of time there before you do that. D-glucose is a D-fructose, I'm sorry, is a keto hexose. It also has C6H12O6. It's found in fruit juices and honey. In the body, fructose will convert into glucose. And again, as we saw in a couple of those earlier pictures there is our ketone group. And again, our 6 carbons, they're there. And once again, this particular case, this is D because of our OH there on the right. Galactose, another one, again, that you should be familiar with, maybe to recognize. Galactose is an aldohexose. It's not found free in nature. It's obtained from lactose, a disaccharide, when you kind of break that apart. It's very similar to glucose, except at carbon number 4, where the OH is located. And again, carbon number 4 would be here. That's 1, 2, 3, and 4. So that would be, again, carbon number 4 has a different spot where the OH is located. You're not going to have to draw. You're not going to have to draw the structure, I don't think, too much. But that again is fructose. Let's talk a little bit about the cyclic structure of monosaccharides. This you will have to draw, so I guess I shouldn't have said that. You might have to draw it from one of these, maybe. So these guys, sort of in the straight chain, can kind of close in on themselves and make more of a cyclic ring type structure, are these sugars. And really, they will make one of 2 rings that look very similar to organic rings there. The guy on the left there looks like cyclohexane, except it has 1 less carbon because there's an oxygen actually in the ring. So this guy actually only has 1, 2, 3, 4, and 5 carbons. This guy over here, which looks like cyclopentane, actually only has 4 carbons, also because there's an oxygen that ends up in the ring. 1, 2, 3, and 4 carbons. So when we kind of draw these guys in their cyclic form, it's going to probably end up in one of these 2 rings. And we're going to talk about how to put everybody on there in a second. And for example, a lot of times this will occur from your last chirocarbon, which if you have a hexose, will most likely be at carbon number 5. And it typically will attack, you got all these carbons. So this kind of bottom carbon will typically come and sort of attacks, attack over there at the carbon oxygen double bond. So that's always sort of where it's going to happen. And for a aldehyde, this will be at the top, right? Now, if you have a keto type group, your attacking is actually going to occur at carbon number 2, because that is where the carbon oxygen double bond is located. So that's always where sort of these guys close in on each other, is at that carbon oxygen double bond. And again, for those aldose, it's going to be pretty much carbon number 1, but for their ketose, it's going to be carbon number 2, where you have that sort of carbon oxygen double bond. Now, what happens is it will form a stable cyclic hemiacetal. If you remember, we talked about hemiacetals in the other chapter, and that is where we have basically a carbon that has an OH, right? And we have an oxygen carbon group, right? And we have a hydrogen, and that is, again, a hemiacetal. And when the carbon oxygen group and the OH are part of the same molecule, for hexoses, that's going to be, again, like I said, carbon number 5, that's going to happen. And the cyclic structure of the D isomer will have that last CH2OH above the ring. So if you remember, kind of when we have our guys look like this, this guy on the bottom, which is furthest away, this guy always ends up kind of upper left corner of the ring, and it ends up to the left of the oxygen in the ring, and it's not in the ring, but it's attached to that sort of carbon on that ring. So that's where that group always sort of ends up, the guy that's on the bottom. So let's talk about how we actually do this. So let's talk about the steps. So let's just make up a fake carbohydrate here to draw. Why not? And we'll just make up some spots here just for fun. Why not? H. So let's say we have this carbohydrate here and we wanted to kind of draw it in its ring form there and kill the ring there. Let's put it back together. Go HO. All right. So the first thing that you really want to do, we're going to turn this into a ring structure, is I would number your carbons. And again, this is going to be carbon number 1, this is going to be carbon number 2, carbon number 3, carbon number 4, carbon number 5, and carbon number 6. So you could do one of two things. You could take this thing basically and just drop it on its side. So you're just going to take this guy, you're just going to drop it down. So you're going to redraw it, kind of tilt it to the right there. So it's going to do that. And again, and we'll have our CH2OH. Again, you could renumber if you like. So this again is carbon 1. This would be 2, 3, 4, 5, and 6. So again, pretty much all I did is just take it and just dropped it down. Yeah. When I do that and I drop it down, everybody that's on the right-hand side here will end up down, right? Right, so as it falls, everybody on the right is going to go down. Everybody on the left-hand side is going to end up, right? And as it falls. So we could put in everybody here. So that is OH, that's H, that's OH, and that's OH. That means that's an H, an H, an OH, and an H. Any questions on that so far? So when this thing closes on itself, because this is a hexose, it's really going to be that last chirocarbon, which is carbon number 5. And this guy is going to go and find where the carbon oxygen double bond is located. Now, this move right here is important because it will tell you which one of those two rings we should draw. So this is how you can figure out how many carbon ring you should draw. You basically just count the carbons you just put into the ring. So that is 1, 2, 3, 4, and 5. So that is 5 carbons that's going to make up this ring. Now remember our choice there, right, is this guy or this guy. And obviously we're going to start with the 5 carbon ring. So that again is how you can determine which one of those two you should draw. Basically find the 2 carbons that are going to come together and just count the carbons that are between there. And if you do that, I'm going to start with that ring and we'll go. And again, it is like the cyclohexane ring. You just got to remember to incorporate the oxygen in there. And that's sort of good place to put it, just to put it right there up on the top right corner. Technically, it doesn't matter where you put the oxygen, but just to keep orientation and kind of following the same steps, I would always kind of put it right there at that spot. What we just talked about, right, is that last guy down here, which ended up here, will always end up to the left of that oxygen, which again is why you might want to put it always in the same spot there. It's going to end up here. So that group is going to end up on top. And I know that is carbon number 6. So at this point, what you might want to do is actually renumber your carbon ring here. So I know this is 6. Then we're going to come down to here, which means that's got to be 5. And we're going to actually go counterclockwise away from the oxygen. That would be carbon 4, carbon 3, carbon 2, and carbon 1. Any questions on that? So again, having that oxygen upper right, knowing the CH2OH goes to the left of it, and using that to kind of number counterclockwise as you come in there. So what is left? Well, what is left is just got to throw some OHs on there and we're done pretty much, yeah. So by doing this, what we're going to do is, and we'll see a picture of it in just a bit, but we're going to actually skip carbon number 5 because carbon number 5 and carbon number 1 come together to kind of close the ring. It actually ends up over in this area of those guys over there, technically speaking. So what we're going to do then is go to carbon number 4. And at carbon number 4, my OH group is up or down? It is down. So I'm just going to throw my OH group down, right? At carbon number 3, my OH group is up. I'm going to throw my OH group up. And at carbon number 2, my OH group is down. So I'm going to go down in this case. That leaves you the last one. And the last one really is based on what you're asked to draw. So there's two types of what is sometimes referred to as anomers. And there's the alpha or the beta sort of anomer here. So alpha is down and beta is up. So if you're asked, for example, to draw the alpha anomer of this guy, that last guy would be the OH down. Now, if you were asked to do the beta, it would look exactly the same. And you would go there, we would go there, we would go here. And if we were asked to draw the beta anomer, OH is going to go up in this case. By the way, just for simplicity, most of the time when people draw this, they don't put anything on the other end. On the other end, it's still a hydrogens. Yeah. So the hydrogens are still there, but just for simplicity, it doesn't get all crazy looking with all the hydrogens. Sometimes people will leave those hydrogens off the other end of it, but they're still there. So that's what's on the other end of it. This is a case where a straight line is actually not a methyl group. It's actually a hydrogen at the end of it. Any questions on that there? Not too bad, right? Drop it on the side and draw it, I suppose, right? So why don't you try one here? Why don't you do, why don't you try this one here? Okay, so let's take a look and see. So we're going to number our carbons. So obviously we want to number up here near our functional group. So it's going to be 1, 2, 3, 4, 5, and 6. Once again, here, if you like, you can drop it on its side and we will end up with this. We will have, put a carbon this way. Then we have that. Spread it out a little bit. And then we got our carbon, hydrogen, and OH. Again, if we sort of number it this way, 1, 2, 3, 4, 5, and 6. Once again, when we do that, basically everybody on the right goes down. So we'll go over here, carbon number 3, and we got an H, and an H, and an OH. Up there on top, we got the opposite there, H, OH, and OH in this case. Again, in this case, it's going to be really that last chiral carbon is going to come in. So that's going to be our carbon number 5 in this case, or whichever one's really the last chiral carbon down the chain. That's going to always go to the carbon oxygen double bond in this case. Yeah. So always to that spot. So this again is going to allow us to now really figure out which of those sort of rings we should draw. That is 1 carbon, 2 carbons, 3 carbons, and actually 4 carbons only. So we really should start with that cyclopentane looking chain that has 4 carbons. And this is really the one that we should draw. Look something like that. Yeah, in this case. Any questions on that? Just like normal, even though it's a smaller ring, this guy is going to end up to the left of my oxygen, right, on the ring. So that is going to end up here. That is going to give me a 6, a 5, a 4, a 3, a 2. And we see that we have not just one group not part of the ring, right? But we actually have 2 that are off of the ring. And that, by the way, is where that guy's going to end up eventually, is off the ring there. We will still continue like normal. In this case, we're still going to skip number 5 because that's, again, basically where the ring came together. So we will go to number 4. And number 4 here, we can see our OH group is up. So we'll do an OH up. Here it is up on 3. Now, in this case, our last OH is determined by what we want to draw. In this case, it is the beta anomer, right? And beta means up. So our last OH is going to go here. But in this particular case, what should go on the other end of it? Yeah, there's this guy here that's off the ring. That's what's going to go on the other end over here, and that would be your carbon number 1 in this case. Now, if you had to do the alpha, everything would look the same except the last one would just be flipped. The OH would go down, the CH2 would go up. So in this case, because of the ketose group there, we actually end up with a smaller ring. Any questions on that there? Now, what happens if I had one like this? We'll go this way. We'll go that way. It'll be different. We'll go that way. We'll go that way. And let's say I wanted to draw the D isomer of this guy here, right? Can I open the ring? Odds are I hopefully can. So let's see how we can kind of work our way backwards. I know for sure if I start counting some carbons, that might be a helpful thing, right? So I know hopefully this is 6. We'll see how we do. That's 5, that's 4, that's 3, that's 2, and that's 1. So I know it is a 6 carbon guy, right? So I do have 6 carbons, which seems like a good place to start. I don't run out of room. It's a good place to start. If you had to venture a guess, is this a aldose or a ketose? I refer you to the previous 2 drawings we did. That was an aldose. That was a ketose. What is different between them? Yeah, the ketose has 2 carbon groups that are off the chain, right? The aldose does not, right? It has just the 1. So in this case, if you had to guess, probably a aldose. Yeah, so that's going to be our group here. Otherwise, we most likely would have somebody hanging off over there on the right-hand side of the chain. And you might even have a smaller chain happening as well if you had that sort of thing going on. All right, well, we might as well number our carbons here. 1, 2, 3, 4, 5, and 6. We know for sure that's our 6, so we could kind of fill that guy in for sure. Now, what we do know is starting at carbon number 2, which is right here, my OH group is up. And that means it originally started on the left or the right to end up. Now to be on the left, right? Because when it fell, if you're on the left, you go up, right? So because that's up, I know that OH group there at carbon number 2 should be on the left. And that means I should have a hydrogen over there. Going to carbon number 3, I see my OH group is on the bottom. And again, when we dump that thing on its side, things on the right-hand side will end up on the bottom. So that would tell me my OH group there at carbon number 3 probably should be on the right-hand side. Going to carbon number 4, I see my OH group is up. And that also means it's on the left-hand side. What about my last carbon there, carbon number 5? Which side should the OH go on? I want to draw the D isomer, which means the last OH should go on the right-hand side, yeah, for the D. And there it is. I just opened my ring up there, yes, by going backwards. So you can go both ways. And again, I would say if you do not see anything hanging off the right-hand side of your ring, it's probably an aldose group up there on top. If you do, then you probably have more of a keto group up on top. And you just kind of want to go that way and just remember again, basically, as you drop that thing on its side, anybody on the right-hand side goes down. And again, anybody on the left-hand side will go up. So it kind of works both ways depending on what you're doing. Any questions on that there? All right, so again, here's those steps we just talked about. Gonna number your carbons, Gonna drop it on its side. And again, everybody on the right goes down, everybody on the left goes up. We're gonna have that connection between our 5 and our 1 in this case to close the ring. And again, you could count up how many carbons you need and which ring to start with. Remember, when we're doing this guy, as we talked about and saw, always ends up to the top left of our oxygen. And that's a good sort of numbering point for your carbons as well. So if you're not sure how many you have, you could just start counting the carbons around and see where you should start your numbering at. And again, if you're asked to draw the alpha anomer, that last OH group there on the right should go down. If you're asked to draw the beta, it should go up. And obviously they will tell you if you're asked to do which one they want you to draw. Just like if for some reason you had to open the chain, they would tell you to do D or L as to where to put that sort of last OH group on that carbon. This does form a cyclic hemiacetal. And again, we have our parts here, our OH, our H, and our oxygen carbon group in our cyclic hemiacetal. That's also a chirocarbon that's formed. And as you can see, basically our OH here gets incorporated into the ring. And we do have like the hydrogen actually shift over, and that's how we get the OH group over there. So that's why we do kind of skip 5, as that's all part of kind of making the ring and closing the ring. So things get kind of shifted a little bit along the way. Now, when we have alpha D-glucose or beta D-glucose, it does kind of open and close along the way. And most of the time, as you can see there, 64% of the time, it's in the beta form on the right versus 36% of the time there, it's in the alpha form as it continues to kind of opens and closes the chain. As we saw in the one we did as well, if you got something that's got a ketone group, you're going to get kind of that smaller ring that's going to have this guy and this guy closing it, leaving these two guys off. And again, that is how come we end up with 2 carbon groups off of the ring there. And again, if it's alpha, the OH goes down, the carbon group goes up, and if it's beta, it's the opposite way around. All right, so why don't you draw this one here, alpha. Okay, so let's take a look. So once again, we're going to number here 1, 2, 3, 4, 5, 6. You could redraw it on the side, or just remember, as we've been talking about, everybody on the right will go down, right? And everybody on the left will go up. So, I mean, if you want to redraw it, you can, or you could just remember that. It's kind of the same idea. We do know that it is going to be, in the case of 6 carbons here, that last chirocarbon, which in this case will be carbon number 5, it is going to go and find that carbon oxygen double bond. Once again, that's going to allow you to count up how many carbons you need for your chart there. That's going to be 1, 2, 3, 4, and 5. So again, that's going to be our 5 carbon ring. That looks like cyclohexane, but obviously has the oxygen inserted in there, and that is a good place to perhaps start it. We always know this guy at the end there is going to end up to the top left of the oxygen, so we're going to go there. That also is going to give us our basis for numbering everybody. So that is carbon 6, carbon 5, again going counterclockwise, 4, 3, 2, and 1 in this case. Any questions so far? All right, now we just got to kind of assign OHs. And once again, we are going to skip the carbon that kind of goes into the ring. And we're going to start with carbon number 4. There I see my OH is on the left, which means when I dump it on its side, it's going to go up. So we're going to go up on that guy. Here at carbon number 3, also have the OH on the left, which when I dump it on its side will go up. So that guy will go up. And lastly, here on carbon number 2, we have the OH on the right, which when we dump it on the side will go down in this case. My last OH, which is on carbon number 1, should go up or down? Should go down. And it should go down because we're asked to draw the alpha here, right? If we were asked to draw the beta, we would pop that guy going upwards. Any questions on that there? Okay. And that looks, say it again. It was, I believe, it has the aldehyde group up on top and has 6 carbons, so that would be an aldohexose would be its classification of it. Yeah. Its true name would be galactose. Yeah. Other questions? Okay. Let's talk a little bit about some chemical properties of carbohydrates. They are what are sometimes referred to as reducing sugars, and reducing sugars gives that oxidized groups to our carboxylic acid, much like we saw in organic chemistry. You could use something like the Benedict's reagent to basically, this is what's happening, right? It's our guy going to our carboxylic acid, right? So it's going to be oxidized, right, as it gains the oxygen, and it will reduce our copper from blue to that reddish orangey color that you've seen a couple of times, I think maybe in lab as well. Pretty much most sugars are reducing sugars, except for sucrose is not a reducing sugar, but most of them are. Because they're able to do that. And as you can see here, our glucose will oxidize, and it really is the exact same reaction we talked about in organic chemistry when we oxidize an aldehyde to a carboxylic acid, right? So that right there is our carboxylic acid group. And obviously that's our aldehyde group. So this is that kind of second oxidation where we insert the oxygen, right? Rather than the hydrogens coming off. And it will make an acid in this case, not so important for us, but again, it produces sometimes we're referred to as sugar alcohols, but not all that important for us at all. All right. So the product here, which you would not have to do, but if this was oxidized, we're just going to basically pop a O in there, and everything else is going to be the same, basically, right? And we're going to make that carboxylic acid, and again, everybody else here would be the same. Like it. And it does exactly what they did in organic. This looks like an alcohol, right? That gets oxidized to an aldehyde. That gets oxidized to a carboxylic acid, right? And the reduction of all those is still the opposite way, right? You're just going to basically go back the other ways. So again, that is sort of our alcohol there, and our carboxylic acid again that you could get here in this case. All right, I think that's actually a good place to lay it up there for today.